In this video, we're going to finally start doing some calculus, namely the differential calculus. What we're going to do is lay out how Newton is able to take derivatives, what we would nowadays call take derivatives. That is, convert the fluent quantities, or the flowing quantities, into their velocities, or their fluxions. That is, we're going to have some equation in the fluent quantities and convert it to a fluxional equation. And along the way, we're going to lay out what Newton is thinking about in terms of setting up the calculus. We're going to cover infinitesimal quantities. Nowadays, we would just call these dt's. And we're also going to talk about the rules for working with fluxions, or the main theorems for working with fluxions. That is, we're going to talk about the product rule, the quotient rule, and the chain rule, and how we're going to be able to derive these from working with infinitesimal quantities. Let me get right to it and try to convey Newton's fundamental ideas about calculus and about fluxions. And as I've pointed out in previous videos, Newton often thinks of physics when thinking about mathematics, namely the motion of particles. And in line with that, on this coordinate grid here, let me consider the position of some hypothetical particle at some moment in time with that right there, and I'm going to designate its horizontal coordinate by x and its vertical by y, as they normally are. And just to review Newton's terminology here, these symbols x and y are often referred to as the flowing or the fluent quantities. He uses these terms because in the setting of particle motion, when we speak about x's and y's and maybe a z, we never intend these symbols to mean a static quantity, a quantity which is permanent over time. We often talk about these in terms of their changing nature. So the x's and y's are going to be called the flowing quantities, or the fluents. And the second, fundamental piece of terminology here would be the idea of velocity. Now, velocity is, as Newton describes it, it's just as what we think of it. It's the rate of change of position, let me call it delta x, divided by delta t. It's how much we change or displace with respect to position, divided by how much we change in time. And nowadays, we might notate such a velocity in the x direction as dx dt, or delta x over dt. Newton is going to notate this as x dot. So x dot is going to stand for the velocity in the x direction. And correspondingly, y dot is going to stand for the velocity in the y direction. And these two quantities here, instead of being referred to as fluent quantities, these are called fluxions. So if I say fluxion, that's essentially synonymous with velocity. Fluxion is just Newton's word for this stuff. So those are the two fundamental pieces of terminology there. And the fundamental insight here is that if we consider this particle located right there, and we ask at some later point in time, where does that particle move to? Can we map its coordinates over that small change in time? What we're going to do in terms of notation is, let's mark the position of that particle there after having moved over some instant in time. The fundamental question to ask is, what is this x coordinate here? What should that be? And also, what should that coordinate be right there? And the fundamental insight here is that it should be x plus some other quantity, which I'll call dot 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 for now. And this coordinate should be y plus dot dot dot. And what should that unknown factor be? That additive factor right there be? It should be estimated by the velocity x dot times some very small quantity in time, which Newton denotes as O. Nowadays, we would say that this additional displacement should be approximated by the velocity times delta t. namely the velocity in the x direction, times delta t. But in Newton's notation, it's going to be x dot times O, where O is some infinitesimally small change in time, which, just to emphasize, nowadays we would refer to this as delta t. So the horizontal coordinate of that particle should be x plus x dot O, and the vertical coordinate should be y plus y dot O. And this is really the fundamental insight here, that x gets a little boost and it moves to x plus x dot O, and y gets a little boost and it moves to y plus y dot O. And these pair of equations here are really what's going to drive all of the calculus that we're going to talk about in this video. If you've studied calculus, this is all going to be pretty familiar, that this additional displacement should be a velocity times a small change in time. If you haven't studied calculus, let me give you a little intuition about what's going on here. So some velocity is always going to be in the form of a change in position divided by a change in time. So this equation, the velocity, let me call it the velocity in the x direction, is always going to be delta x divided by delta t. Now, what is delta x? Just rearranging this equation. Delta x is going to be given by the velocity in the x direction times delta t. That is, if I want to approximate what delta x is going to be, what I should do is first find its velocity in the x direction and then multiply it by delta t. And then to go from here to this, it's just a change in terminology, really. The small quantity that we want to find is precisely delta x, and v sub x, the velocity in the x direction, in Newton's notation is going to be designated as x dot, and then this delta t is going to be simply O. Let me show you how that simple idea of considering x dots and O's is going to cash out in terms of finding fluxions now. Let's say I have some particle, and its motion is described by the following equation. That is, its y-coordinate is always the square of the x component. And graphically, we would say that if this is the xy coordinate grid, then it moves in a parabolic manner. And now let's use those ideas. Let's transform x into x plus x dot O. That is, we start at some position x, and then we ask what happens just a moment later. And then I transform y into y plus y dot O. In other words, I'm going to substitute x plus x dot O in for x, and I'm going to substitute y plus y dot O in for y in this equation. So let's do precisely that. I substitute y plus y dot O. That's still going to be equal to x plus x dot O all squared. And now I know what y is. Y is just equal to x squared, so I'm going to make that substitution. So I have x squared plus y dot O is equal to, and now what I'm going to do is just square this equation. So I'm going to have x squared plus 2 times x dot times O. And then I have that second term squared, which is going to be x dot squared times O squared. And now I notice immediately that I have x squared on that side, x squared on that side. So I'm just going to cancel that stuff there. And now what I'm going to do is a little bit of algebra with these infinitesimal quantities. Now, in Newton's conception of all this stuff, this quantity O is never equal, it's never exactly equal to 0. And by the way, when I notate 0 in this video, I'm going to mark it with that slash there just to avoid confusion with O. This O is never equal to 0 exactly. And if it's never equal to 0, that means I can divide both sides by O. So I have that right there, and I'm going to divide the rest of this stuff by O. And what I get as a result is y dot equals 2x x dot. Then I have that last term there, which is plus x dot squared O. And now here's the next major insight here. Newton wants this quantity O to be as small as possible. He wants it to be infinitesimally small. That is, he wants it to be smaller than any number you could conceive of. And then he asks the question, what is y dot going to be as this O thing is infinitesimal? And the answer to that question is, if you know calculus, this O, in the limiting sense, causes this second term to be ignored in the long run. That is, as O, I'll write it like this, as O goes towards 0, y dot goes toward the quantity 2x x dot. So in a limiting sense, as this O quantity that's infinitesimal goes towards 0, this y dot goes toward 2x x dot. So now I have the fluxional equation, which is y dot equals 2x x dot. And now, if you know some calculus, you might be saying, but wait, I know that the derivative of x squared is just 2x, but here I see 2x x dot. What's going on there? To convert this to our modern notation, y dot would really be dy over dt, and x dot would really be dx over dt. So that's what this equation is saying in our modern notation. I guess you would say the Leibnizian notation. And then, if you wanted to find what dy divided by dx is going to be, what you would do is you'd want to solve this equation for y dot divided by x dot. And if you do some rearranging with this equation, you'll find that y dot divided by x dot is going to be 2x. And this y dot divided by x dot quantity is the slope of the tangent line at any x value. So hopefully you can see how these ideas do cash out in terms of finding the equation relating the fluxions of x and y from the original fluent equation. At this point, it's also worth pointing out some of the philosophical difficulties that come with arguing with infinitesimals. And one guy who really criticized Newton for doing this sort of argument here was Berkeley, also a very prominent philosopher. What he said was that Newton is demanding two things which are in contradiction. First, if we go back up to this step here, notice that we divided by O. And to divide by a number, it has to be the case that this denominator is not equal to 0. So we want this O quantity, whatever it is, this O has got to be non-zero. But after I divided by 0, look at what I've done here. I've just neglected that term there. So that means in this step, I'm really considering O to be equal to 0 because I just neglected that term. There's no way to neglect that term if O is not equal to 0. So these two statements here are in contradiction with one another. And this turns out to be a very good criticism. After all, it can't be the case that O is simultaneously non-zero and 0. And this is really why in modern analysis, you don't really talk about infinitesimals anymore in the rigorous sense. You may talk about them in the sense of a teaching tool that might make things a little bit more intuitive. But the way we argue for this sort of thing nowadays is to use limits. And you can notice that I was essentially doing precisely that. I was using a limiting argument. I was saying that in the limiting sense, as O goes toward 0, this quantity y dot goes toward this quantity. So I just want to point that out, that our modern conception of derivatives, and I guess you would say of fluxions, is not quite what Newton's conception is. Even though I'm bashing Newton for using infinitesimals, I will point out, though, that when you use these infinitesimal arguments, you get the same result as what you can prove using limits. So in terms of doing computations, these infinitesimals are perfectly fine. And as teaching tools, they're perfectly fine. You get nice results. And let me continue that line of argument by showing you one pretty simple result that everyone learns in calculus, which is how to take derivatives or how to work with the fluxions of sums. That is, let me introduce another fluent quantity, let me call it z, and I'm going to define z to be the sum of two other quantities, x and y. And I'm going to use the same transformation that I've been using. X goes to x plus x dot o, y goes to y plus y dot o, and analogously, z goes to z plus z dot o. And now what I'm interested in is finding what z dot is going to be. I have these x's and y's, and I want to find the velocity of z, the fluxion of z. So let me apply these transformations, or let me substitute them into the equation. I get z plus z dot o, and that's really the quantity that I'm after, that z dot. That's equal to x plus x dot o plus y plus y dot o. And then z is equal to x plus y. So I could substitute z is equal to x plus y, and what I'm going to get is that cancellation. Those three terms disappear, and what I'm left with is z dot o is equal to x dot o plus y dot o, and then I divide both sides by o. I'm going to use the same line of argument. On the left-hand side, I get z dot, and on the right-hand side, I get x dot plus y dot. So there you go. That proves that the fluxion of z, z dot, is simply the sum of the fluxions of x and y. That is, when I convert this equation to the fluxional equation, it's just as we know how to take derivatives. You take the derivative, or you find the fluxion of each of the terms individually, and then sum them to get the fluxion of z. That might be a bit boring, but let me now prove a more interesting rule that we're going to use for the fluxions, which is the product rule. And I'm going to do a similar thing. I'm going to introduce this fluent z, which is going to be defined as the product of the fluents x and y. And once again, I'm going to apply those transformations. X is going to go to x plus x dot o, and y is going to go to y plus y dot o, and z is going to be z plus z dot o. So let me write that in here. Z is going to be z plus z dot o. That's equal to x plus x dot o times y plus y dot o. And then I'm going to multiply out this right-hand side. I get x times y. Next, I'm going to get x y dot o. So x y dot o. And next, I'm going to write it in the order x dot times y times o. So that's x dot y times o. And then my final term, that's going to be x dot times y dot times o squared. So it's x dot y dot o squared. And that's still equal to z plus z dot o. And again, z is equal to xy. So I just cancel that term with that term since they're equal. And then I'm left with this equation. Z dot o is equal to these three terms on the right-hand side. And then I'm going to divide both sides by o. Divide that side by o as well. And on the left-hand side, I get z dot, which is the thing I'm after. Z dot is going to be equal to x y dot plus x dot y plus x dot y dot o. And then I use that limiting argument. I say that as o goes toward 0, z dot is going to go toward, or it's going to be, in the limiting sense, equal to x y dot plus x dot y. And there you go. There's the product rule of fluxions or of derivatives, derived very simply using infinitesimals. Before working with some examples, let me prove another very important rule for working with derivatives, which is the quotient rule. And I'm going to proceed in a similar manner. I'm going to create this fluent z, which is going to be defined as x divided by y. Two other fluents, x and y. And before substituting those transformations immediately, what I'm going to do is rearrange this equation. I'm going to solve for x. I'm going to find that x is equal to y times z. And the reason that I'm going to do this is because I already know how to work with products from that rule that I just derived. So this equation, x equals y times z, implies that the fluxional equation is going to be x dot is equal to y times z dot plus y dot z. And now I'm going to take that z there and substitute back in x divided by y. So I have y z dot is plus y dot x divided by y. And that's still equal to x dot. And now what I'm going to do, I'm going to multiply both sides of the equation by y, just to clear out that denominator. On the left-hand side, I have x dot y. On the right-hand side, I'm going to have y z dot times y. So that's going to be y squared z dot. And then for the second term, the y's cancel. And so I just have plus, I'm going to write in the order x y dot. And again, the fluxion that I'm after is really z dot, which is right there. So I just solve for z dot now. What I'm going to do is I'm going to move this quantity onto the left-hand side. So I get x dot y minus x y dot is equal to y squared z dot. And then I divide both sides by y squared. And then what I'll find is that z dot is this quantity here, x dot y minus x y dot divided by y squared. And there you go. There's the quotient rule derived very simply. Just for fun, let's work with a few examples. And one example I'd like to do is the example where y is equal to the square root of x. Now, you can view this in two different ways. You can view this as the square root of x, also meaning that we have x to the 1/2 power. And then you can try to prove the product rule for fluxions or for derivatives, and then you can work with that. Another thing you can do is you could square both sides of the equation to obtain that y squared is equal to x. And the advantage for in doing this is that we already know how to work with this sort of equation in fluents. From that calculation, we had y is equal to x squared, but this is just changing symbols around. And we found that working with that equation, that converting to the fluxional equation, we should have this, that 2y y dot is equal to x dot. And again, the quantity that we're after is y dot. So let me solve for y dot. I find that y dot is equal to x dot divided by 2y. And then I know what y is equal to. It's the square root of x. So let me just substitute that in again. And what I have is that y dot is equal to x dot divided by 2 times the square root of x. And writing this in our modern notation, if we want to find what dy over dx is going to be equal to, this would be, in Newton's notation, y dot over x dot. And when I do that, I'm going to find that y dot over x dot is 1 divided by 2 square roots of x. And another way of writing that is 1/2 times x to the minus 1/2. And again, if you know calculus, this should be no surprise. That exponent comes down to the front. We get 1/2, and then we subtract 1 from that exponent. So the derivative, or the fluxion, of x to the 1/2, or the square root of x, should be 1/2 times x to the minus 1/2. Just pointing out here that we can work with the algebra of these symbols, or we can work with the power rule. Another property of the algebra of fluxions, if you will, is the chain rule, or what we would nowadays call the chain rule. And Newton uses a couple nice examples in the text, which are a bit lengthy, but the main idea is going to be distilled into the following example. Let's say I have y is equal to the square root of x squared plus 1. And now I don't really have a good rule for working with this as it's written. But Newton observes, what if I make a clever substitution? Let's say I have u being equal to that inside stuff. Let's say u is going to be equal to x squared plus 1. So now I have two equations. Now just making that substitution there, x squared plus 1 is equal to u. I have that y is equal to the square root of u. And I have this equation here. But the advantage of this is I now know how to work with this equation, and I know how to work with this equation. In the previous example, I showed you how to work with this equation, and I showed that y dot is equal to u dot divided by 2 square roots of u. And now we've already had some experience with this equation, or equations of this form, and we would find that the fluxional equation is going to be u dot is equal to 2x x dot. And by the way, I haven't proven yet that the fluxion of, let's say, 1 is 0, but you can prove that on your own. That's very easy to show. Nonetheless, I get this following fluxional equation. And now I go back to this equation. I notice that there's a u dot there, so I'm going to substitute u dot is equal to 2x x dot into that equation. And what I'll find is that y dot is equal to 2x x dot divided by 2 square roots of u, but now I know what u is equal to, it's x squared plus 1, so I'm going to substitute that back in. So I get the square root of x squared plus 1. And then finally, I cancel out those twos there, and I find that y dot is equal to x dot divided by the square root of x squared plus 1. And again, if you already have some experience with the chain rule, this is not surprising at all. What we would do nowadays is we would say that y is equal to x squared plus 1 to the 1/2 power. And then I would say that the inside stuff, or what I call u there, is going to be x squared plus 1. And then I use the power rule first on the outside stuff, so that I guess I'd say y prime is equal to 1/2 x squared plus 1 to the minus 1/2 times the derivative of the inside stuff, which is just 2x. Cancel out the 2's, and I'm left with exactly what I had there. And again, just to emphasize this y prime, or dy over dx, this would really be equal to, in Newton's notation, y dot over x dot. So it is actually equal to this stuff here. One thing I'd like to share with you from the text, and it's something that's probably unknown to you, and it was unknown to me before I read this section of the text, was a very interesting tabular method for computing derivatives, or computing the fluxional equation. And let me take the example, y minus, let's say, x cubed minus x squared plus x is equal to 0. And first of all, to do this method, to find the fluxion equation from this, we're going to have some algebraic curve, what I refer to as an algebraic curve, being set equal to 0. And then what we're going to do is we're going to take note of how many fluents we have. We have 2 fluents. We have the x's and y's. What I'm going to do now is create a table. I'm going to divide it into 2 parts because we have 2 fluents. On the left-hand side of the table, or this first row here, this is going to be the x side of the table. And on the right, I'm going to have the y side of the table. And here's what I'm going to do. I'm going to take these 4 terms, and I'm going to group them according to what power in x they represent. So in the x's, I really have up to the 3rd power in x. So I'm going to write the 0th power of x. I'm going to write it like this. Newton doesn't do it, but I'll notate it like this. I have the 1st power in x, the 2nd, and the 3rd. And in the y's, I have only up to the 1st power. So I'm going to have 0th power, and then the 1st power. And then I'm going to stick each of these 4 terms in the appropriate location on the table. Let's first deal with this first row. What are the 0th degree terms in x? The only term that fits that criterion is y. And next, what is the 1st degree term in x? It's only that term, x, so I'm going to write it there. What is the 2nd degree term in x? It's just that term, which is minus x squared. And then finally, the 3rd degree term in x, which is minus x to the 3rd. So I've just grouped these terms according to which category they're in the x degrees. And then I'm going to do the same thing in the y degrees. Which of the terms is 0 degree in y? And it turns out there are 3 terms that fit that criterion. We have minus x to the 3rd, minus x squared, and positive x. So I'm going to put them right there. And then I have a 1st degree term in y, which is just y. I'm going to write that there. And here's what I'm going to do. I'm going to, on the left-hand side, this x side, I'm going to multiply each of these 4 terms by x dot over x. So I'm going to write that 4 times. X dot over x. And then same thing for these 2 terms, except I'm going to multiply them by y dot over y. Y dot over the y. And the last thing, the last step to setting up this table, is to look at the coefficients in front of these x dots here and these y dots. And what Newton observes here is that the coefficients must be in what's called an arithmetical progression, meaning that the increments from one coefficient to the next has to be a constant value. And what's really nice about this method is that I can choose any arithmetic progression. Simply put, I could start with 0 here. I'm going to let the coefficient be 0 there. But once that's set to be 0, this next one to the left has to be 1. The next one to the left has to be 2. And then this final one has to be 3. So you see here that I sort of chose that first one to be 0 times x dot over x. But the next one had to be 1 times x dot over x. The next one had to be 2 x dot over x. And the next one had to be 3 x dot over x. And I'm going to do the same thing for this side here, for the y's. I'm going to choose this first one to be 0, which means this next one has to be 1, because I want to move in constant increments. So I have 0, 1, 2, 3 over there, and I just have 0, 1 over here. And now what I'm going to do, I'm going to multiply this term by this term, this term by this term, this term by this term, and so on. I'm going to do that for all 6 columns of the table. So what do I get for this first multiplication? Get minus 3 x squared x dot. The next term is going to be minus 2 x dot. this term here is going to be plus x dot, and then this term here is going to be 0 because I'm just multiplying by 0. And then for this other one, I'm going to have y times this, which is going to be plus y dot, and I just have 0 here. And what you're going to do is you're going to take all these terms and once again set them equal to 0. And Newton says, there you go, there's your fluxional equation. And you can notice here that this is correct. Y goes to y dot, minus x to the third goes to minus 3x squared x dot, minus x squared goes to minus 2x x dot. Then I have plus x that goes to x dot. But what's really cool about this method, it's kind of interesting, is that once again, going back to these coefficients, I didn't have to pick 0, 1, 2, 3, or 0, 1. What I could have done is, instead of 1, I could have let this first one be 0 x dot times x, but that means that this one right next to it has to be 1 times x dot over x, and this one has to be 2 x dot over x. And the one to the right is going to be, as you might guess, negative 1 x dot over x. And then you'll find that if you do this multiplication in the exact same ways that we just did, you'll get the exact same thing coming out. And once again, you can choose your 0 point or whatever you want to do at whim. I could have chosen this one, this first one, to be 0 y dot over y, but that would mean that this one to the right of it, 1 degree less, would have to be minus y dot over y. And if you multiply all this stuff out, you're going to find that you get the exact same answer. And it's quite remarkable. I encourage you to convince yourself or maybe prove in general why this works at all. But it's just something I wanted to share with you since it's probably not known to many people. I think that'll wrap it up for this video. To recap what we've accomplished in this video, we've been given an equation in the fluents, and we were able to convert that to some equation in the fluxions. That is, we've been given some equation in the variables, and we're able to find some equation relating the velocities of those variables. And nowadays, we just call this the differential calculus. And to give you a preview for what's coming in the next video, we're going to try and reverse this process. Given some equation in the fluxional quantities, we're going to try to find the equation relating the fluent quantities. And nowadays, this inverse problem is called the integral calculus. So in this video, we've covered differential calculus, and in the next video, and maybe some other videos, we're going to be covering the integral calculus, which also overlaps with the field of differential equations. And I hope you'll join me for that video. If you enjoyed this video or others, feel free to subscribe to my channel, like the video, feel free to comment as well. And like I said, hopefully you'll join me for the next video. Thanks for watching.